Hello again. In the last lecture, we saw several different ways to visualize solutions of autonomous first-order differential equations. Remember, they were differential equations of the form y prime is some function of y, no t's on the right-hand side. We saw the slope field and solution graphs. We then saw the motion on the phase line. We also used the graph of the right-hand side of the differential equation. In today's lecture, what I do is revert back to some more calculus, use some more calculus for determining the types of equilibrium points. This will be the first derivative test for equilibrium points. And then I'll turn to the main theorem in differential equations. This is the so-called existence and uniqueness theorem, and we'll see how that helps solidify all these qualitative notions. Now, first, remember, we saw three types of equilibrium points. There were sinks, sources, and nodes. Let's look at the phase lines again to see what they look like. So here's the differential equation we saw last time. Y prime is y squared minus 1. Down here we see the graph. The graph crosses the y-axis at 2 points, plus or minus 1. They are our equilibrium points. And we see from the solution graphs that y equals plus 1 is a source. Nearby solution curves move away, whereas y equals minus 1 is a sink. Nearby solution curves come closer to it. There are two of the types of equilibrium points. A third type was the node. Let me turn to the differential equation y prime is y squared. Now we see a single equilibrium point at 0. And since the right-hand side of the differential equation y squared is always positive, all other solutions move up. All other solutions move up. So from below, solutions converge up to the equilibrium point at 0. But above, when y is positive, solution curves move off to infinity. So some solutions come in, others go away. That's a node. Okay, now there could be other types of nodes. For example, if you take y prime is not y squared, but minus y squared, then again we have an equilibrium at 0, but now the slopes are always negative, so solutions would always decrease. Another example is we could have the trivial differential equation, y prime equals 0. There, all solutions are constant. Right? So all of our solutions are equilibrium points, so arbitrarily close to any equilibrium point, we've got nothing else but equilibrium points. And still other things could happen. For example, you could have a differential equation that has an equilibrium point, and arbitrarily close to it are infinitely many other equilibrium points that accumulate on it, but not everything is an equilibrium point. In between, they could be doing something. So let's now turn to the first derivative test for equilibrium. This will be a test from calculus that allows us to determine immediately whether our equilibrium point is a sink or a source. Okay? And then, with that information, we can immediately sketch the phase line. So, here's what we'll do. Suppose we have an equilibrium point at y0. Okay, our differential equations of y prime is f of y, so that means f of y0 equals 0. So the graph of f crosses the y-axis at your point y0. Let's assume that the derivative of your function at y0 is positive. What does that say? Well, that says that our graph increases through y0. So if y is less than y0, then f of y is negative. So for y below our equilibrium point, slopes are negative. That means solutions are moving away. On the other hand, if y is greater than y0, then f of y is greater than 0. That means above y0, slopes are positives, solutions increase. So that says that if the derivative at y0 is positive, our equilibrium point must be a source. And now the exact opposite is true. What happens if the derivative at y0 is negative? Then that says that f of y decreases through y0. So below y0, the f of y is positive. That means the slopes are increasing. Solutions are coming in to y0 below y0. And similarly, above y0, now f of y is negative, so solutions are decreasing toward y0. That says that if the derivative at y0 is negative, then y0 is a sink. Now, the final case, the intermediate case, is where the derivative at y0 happens to be 0. In that case, we get no information. For example, we could have a node. Remember the equation we just looked at. Y prime is y squared. We have an equilibrium point at 0, but the derivative of y squared is 2y, so that's 0 at 0, and we get a node. On the other hand, look at y prime is y cubed. Again, 0 is an equilibrium point, and again, the derivative at 0, 3y squared, is 0, so the derivative is 0 at the equilibrium point. But for y cubed, if y is positive, then y cubed is positive. So above 0, our slopes are increasing. On the other hand, if y is less than 0, if y is below 0, again, y cubed is negative. So again, solutions now are going the other way. That means that for y prime equals y cubed, we have a source. And similarly, if you look at y prime is minus y cubed, again an equilibrium point at the origin, where the derivative is 0, but now we compute a sink. So let's do a couple examples of this. Let's return to our logistic differential equation. Y prime is y times 1 minus y, or y prime is y minus y squared. We see we have equilibrium points at 0 and 1. And now let's use the first derivative test to determine their type. Take the derivative of the right-hand side. The derivative of y minus y squared, of course, is 1 minus 2y, and then plug in our equilibrium points. Take the derivative at the equilibrium point 0. We have f prime at 0 is 1 minus 2 times 0. That's 1. That's positive, so 0 is a source. The derivative at 1 now is 1 minus 2 times 1. That's minus 1. That's negative. So the equilibrium point at 1 is a sink. So effectively, we know everything about the behavior of solutions just from that information. So here's our pictures for the differential equation. Y prime is y times 1 minus y. From the graph of that quadratic function, we know we have roots at 0 and 1, as we just saw. We see the derivative at 0 is positive, the derivative at 1 is negative, and by the first derivative test, then, 1 is a sink. Solutions tend to the equilibrium point at 1. The equilibrium at 0 is a source. Solutions tend away. And now, because there are no equilibrium points in between, we know the behavior everywhere. Solutions between the equilibrium points must always increase. Solutions above y equals 1 must always decrease. And same thing below y equals 0. The first derivative test tells us everything. One more example. How about y prime is y cubed minus y? Or factor out a y there, y prime is y times y squared minus 1. From that equation, you see that we have equilibrium points at 0 and plus and minus 1. So let's again use the first derivative test. The derivative of y cubed minus y is 3y squared minus 1. So just plug in all our equilibria and determine their types. For example, at 1, we get 3 times 1 squared minus 1, that's 2. Greater than 0, 1 is a source. At minus 1, the derivative is, again, 3 times 1 minus 1, 2. That's, again, a source. But at 0, the derivative is 3 times 0 minus 1, that's minus 1. Less than 0, that's a sink. So with just that little bit of calculus, we now know everything that's happening for solutions to that differential equation. Let's look at those solutions. Here again is the graph of our differential equation. The right-hand side has equilibrium points at minus 1, 0, and 1. The derivative at 1, as we just saw, is positive, as it is at minus 1, whereas at 0, the derivative, the slope, is negative. So from the first derivative test, we know that 1 is a source. Solutions move away. Minus 1 is also a source. Derivative is positive there. Solutions move away. And the equilibrium point at 0, derivative less than 0, is a sink. And again, there are no equilibrium points in between these equilibrium points, so we know everything. We know what's happening to all other solutions. And one final example that we visited earlier, let's take y prime is y to the 4th minus y squared. Or factor out a y squared, that's y squared times y squared minus 1. Again, we have equilibrium points at 0, 1, and minus 1. Okay. Now use the first derivative test, and we have a little bit of difference here. For example, the derivative here is 4y cubed minus 2y. That's the derivative of y to the 4th minus y squared. Again, evaluate that derivative at the equilibria. At 1, we just get the derivative is 4 minus 2, that's 2. So 1 is a source. At minus 1, the derivative is now minus 4 plus 2, that's minus 2. So minus 1 is a sink. But at 0, the derivative vanishes. So we get no information. On the other hand, just having the information about those two flanking equilibria tells us everything again. So here is the slope field for this differential equation. We know we have an equilibrium point at 1, right about there, an equilibrium point at minus 1, right about here, and we know that 1 is a source, so solutions run away. We know that minus 1 is a sink, so solutions tend in. So just by looking at this situation, we see what the equilibrium point at 0 must be. Right? So above 0 and below 1, solutions are decreasing. Below 0 and above minus 1, solutions are also decreasing. So that says that our equilibrium point at 0 must be a node. So sometimes you get no information from the first derivative test, but sometimes the information at other equilibrium points help you out. Okay, one other example. How about y prime is sine squared y? Here comes some trigonometric functions. Now, sine is the most basic trigonometric functions. You know that the graph of sine y is periodic with period 2 pi, and that sine y has zeros at 0, and plus or minus pi, and plus or minus 2 pi, and plus or minus any integer times pi. So the right-hand side of this differential equation has infinitely many equilibrium points at plus or minus n times pi for each n. And now also, from calculus, we know that the derivative of sine y is cosine y. So let's try the first derivative test here for sine squared. Y prime is sine squared y. The derivative by the chain rule is 2 times sine y, then times the derivative of sine, that's cosine. So f prime of y is 2 sine y cos y. But remember, sine of y vanishes at all of our equilibrium points. So the derivative is equal to 0 at each of these equilibrium points. So no information at all from the first derivative test. But we're kind of lucky. Look at the right-hand side of the differential equation. It's sine squared y. So at any non-equilibrium point, sine squared y is positive. So solution curves must all go uphill. So we know just by looking at the right-hand side that all of those equilibrium points are nodes. But let's just look at those solutions. So here is the slope field for y prime is sine squared y. And as we just saw, all solutions tend to increase between the equilibrium points. Each of the equilibrium points is a node. So even though the first derivative test tells us nothing, we still know exactly what's happening. But now here's a question. Why can't we have solutions? Say, here's 0, here's minus pi. Why can't we have solutions that increase for a while, climb up the slope field, and then level off at the equilibrium point at 0, run along 0 for a while, and then start increasing up to y equals pi, cut across that equilibrium solution for y for a while, and then decide to just keep increasing again? Why can't we have solutions that cross those equilibrium points? Well, that's governed by the existence and uniqueness theorem for differential equations, probably the most important theorem in the field. Here's what it says for first-order differential equations. Suppose you have a first-order equation, y prime is f of, let's say, t and y, may depend on t and y. And suppose that f of t and y, your right-hand side, is nice at the point t0, y0. I'll explain what I mean by nice in a minute. Then, the existence and uniqueness theorem says two things. First, there is a solution that satisfies the initial condition y of t0 equals y0. Given that point t0, y0, where the right-hand side is nice, there is a solution that satisfies that initial condition. But more importantly, that solution is unique. There's only one solution that passes through the point t0, y0. Now, what does nice mean? Well, nice means that that right-hand side, f, is continuously differentiable at the point t0, y0. Remember what that means. That means you can differentiate f with respect to t and with respect to y at that point, and what you get is a nice continuous function. If that condition holds, then you've got, first of all, a solution through that point, and secondly, that solution is unique. So going back to y prime is sine squared y, we now see that solutions, in fact, cannot cross. Sine squared y is a perfectly nice right-hand side. It's differentiable at every point. In fact, it's continuously differentiable at every point. Its derivative is 2 sine cos. So that means solutions can never cross. So we could never have a solution come up and merge with an equilibrium point for a while and then go on. Now, there's a slight problem. Sometimes your differential equations on the right are not nice, and that causes problems. Let me give a couple examples of that. Let's look at y prime is y divided by t. Where is there a problem here? Well, we've got a t in the denominator. So when t equals 0, the right-hand side isn't even defined, never mind continuously differentiable. On the other hand, we know some solutions to that differential equation. If you look at just the simple function y of t is k times t for any constant k, that is a solution. Take the derivative of k times t, you just get k. Plug it into the right-hand side, you get kt over t, the t's cancel, you get k. So yes, k times t is a solution to that differential equation. But now notice, infinitely many of those solutions pass through 0 at time 0. Y equals k times t always satisfies y of 0 equals 0 no matter what k is. So in fact, you have infinitely many solutions passing through a point where the existence and uniqueness theorem did not hold. And now there are no solutions whatsoever that satisfy y of 0 equals y0 when y0 is a non-zero number. So you have infinitely many solutions through 0 at time 0, but no solutions through any other point y0 at time 0. And something else is a little funny here. Let me turn back to the computer. So here is the slope field for y prime is y over t. And I've used the computer to calculate two of those solutions. Of course, we know what they are. They're just k times t. But look at what the computer gave me. In one case, it gave me a nice straight solution that went right through the origin. Y is k times t. Ooh, there was something funny going on there when we went through 0. In the other case, the solution just gave me half of that line. What's happening here? Well, near that bad point, t equals 0, the computer's numerical method sometimes gets confused. Let me see if it gets confused again. Go down here. No, all the way through. All the way through. All the way through. Whoops, that one didn't go all the way through. The numerical methods given by a computer sometimes go bad when you've got a bad point on the right-hand side of your differential equation. But it gets even worse. Let's look at another differential equation. Let's say y prime is y divided by t squared. Where does that go bad? Well, again, we've got a t in the denominator, so when t equals 0, the right-hand side, again, is not defined. So we could go and solve this differential equation, but let's not worry about that. Let's see what happens on the computer here. So here we see the slope field for y prime is y over t squared. Think of what solution should do when t is positive. Right? T equals 0 is the bad place, but when t is positive and y is positive, then y over t squared is positive. So our slopes to the right should be going uphill. And yes, they are. But look at what the computer has done to this solution here. Yes, as t goes on, that solution should be increasing. But wow, back here near 0, suddenly it's decreasing. Again, the numerical algorithm has gone a little bit crazy at this bad point. Other cases, looks fine there. Oh, look at that. This solution should be going downhill everywhere. Slopes are negative to the right of the y-axis, but somehow our numerical method made an error. So what we see is numerical methods, again, can go wrong at bad points on the right-hand side of the differential equation. So let's actually look at another one. Here's another differential equation. This time it's autonomous. There's no t's. It's y prime is 1 plus y divided by 1 minus y. Where's the bad point here? Well, in the denominator, we have 1 minus y, so when y equals 1, we've got 0 in the denominator. So that means our slope field becomes infinite at y equals 1. We also have a 1 plus y in the numerator, so 1 plus y vanishes at y equals minus 1. We've got an equilibrium point at minus 1. So here's our slope field. Notice that the slopes are pretty nice down here near minus 1. But as we get closer to y equals plus 1, these slopes get more and more vertical. The slopes are infinite at y equals 1. And watch what the computer does when we try to find solutions now. Whoa, is that the solution to the differential equation? Another one. Is that the solution? This numerical method is really going crazy in this case because we've got a place, again, where the denominator is 0. Now, with an eye toward what's coming later, this is actually chaotic behavior. If I start out very close, say to this point, I get one solution. If I move a little bit over and start out, my numerical solution gives me a completely different solution. What's happening is the so-called iterative method is behaving chaotically. This is something that we'll see over and over again in this course when you have, first of all, numerical methods that go crazy. Sometimes they go chaotically crazy. And later, like we saw with the Lorentz equations, often differential equations themselves behave chaotically. So this is the beginning of that other sub-theme in this course. A couple more examples. Let's look at y prime is 3y to the 2/3. Okay, y prime is 3y to the 2/3. Is that a nice right-hand side? There's nothing in the denominator, looks pretty good. But remember, what's the derivative of y to the 2/3? The derivative of y to the 2/3 is 2/3 times y to the minus 1/3. So when y equals 0, we've got a 0 in the denominator of the derivative. The derivative doesn't exist there. Remember, our right-hand side had to be continuously differentiable. So we've got a bad point when y equals 0. Now, we know some solutions here. Obviously, y equals 0 is a solution, right? If you plug y equals 0 into the right-hand side, you get 0. So y equals 0 is a constant or equilibrium solution. Do you know any other solutions? Well, we'll see how to do this in a couple of lectures, but another solution is given by, well, look at the right-hand side. It's 3 times y to the 2/3. The function y of t equals t cubed solves that equation. Differentiate t cubed, you get 3t squared, and that equals 3 times t cubed quantity to the 2/3 power. So yes, t cubed is a solution to that differential equation. But so is y identically equal to 0. So y of t equals t cubed crosses y equals 0 at 0. So we don't have uniqueness for this differential equation. And this is very different from the previous ones where all of a sudden we had points where the differential equation wasn't defined. Here the differential equation is everywhere defined, but it's not differentiable. There's my equilibrium solution, y equal to 0, and now other solutions look like that. Looks just like the graph of t cubed. It crosses my equilibrium solution. That's forbidden if the right-hand side is nice, but if it's not differentiable, it happens. And in fact, infinitely many of these solutions cross our equilibrium solution because y equal to 0 is a bad point. Okay, well, now one more differential equation. Okay, let's take the differential equation y prime is e to the t sine y. That's a nice differential equation, right? The derivative of e to the t and sine y are all nice. So that differential equation satisfies the existence and uniqueness theorem. But now let's go to the computer and see what happens here. There's the slope field for e to the t sine y. Sine y vanishes at y equals 0. So we have an equilibrium point at y equals 0. Kind of hard to see, but if you look over to the left, you see it. Sine y also vanishes at y equals pi. You can see an equilibrium solution right up about here at y equals pi. And now e to the t times sine y for y between 0 and pi, sine y is always positive. So the slope fields are always increasing. So this is a nice right-hand side. We can't have solutions cross. We know we have an equilibrium point at pi and at 0. And we know that solutions are increasing everywhere in between. Let's see what happens when we use the computer to find those solutions. Whoa, what happened there? And what happened there? And what happened there? Clearly, the computer is going crazy. Make a small change in my initial condition, get a very different change in the behavior of solutions. So notice that all of these solutions are fine for a certain time. The solutions just climb up to the equilibrium point at y equals pi. But then eventually they all diverge. Eventually they go crazy. Again, chaotic behavior. Now, one thing to notice is this differential equation has a very nice right-hand side, right? The exponential of t times sine y, that's perfectly differentiable, continuously differentiable. So that differential equation satisfies the existence and uniqueness theorem. What's happening here? Why are we seeing this chaotic behavior? Why is the numerical method breaking down? Well, the fact is that there are lots of different numerical methods out there, but given any numerical method, you can always find a differential equation, usually very easily, that will break that numerical method. These numerical approximations usually are fine, but often they can break down. We'll return to this idea of numerical methods in Lecture 6. In the meantime, I'm going to return to our other sub-theme, namely bifurcations. That will be the topic of the next lecture.